Right, hello, welcome to my channel. Right, I've made this classic NAND gate oscillator. It's a relaxation oscillator using NAND gates. I've used all 4 NAND gates, but anyway, one is enough. It a square wave oscillator. Right, it uses a resistor and a capacitor on the input and output of a gate to produce a square wave. Right, I'm going to demonstrate how you can use a Mosfet as a capacitor. The gate to drain and source insulation can be used as a capacitor. However, I'll show you the range of capacitances. I've measured a number of MOSFETs, enhancement MOSFETs, and I've found out that the range normally is below 10 nanofarads, somewhere from 0.1 to about 0.1 nanofarads to around 6-7 nanofarads. Right, one, you have to actually bridge together the drain and the source terminals, so that you can actually have an increased capacitance. Okay, there are 2 capacitors, of course. If you check the literature on MOSFETs, the capacitance of MOSFETs, they call them the stray capacitances, but yeah, you can actually use them as a capacitor, as a component in your circuit. Right, so I'll demonstrate first with a capacitor. This is, I think this should be a Mylar capacitor, Mylar or polypropylene capacitor. And its value is 2.2 nanofarads, and that's a 4093 IC there, which is a NAND gate. 4 NAND gates IC. Right, the resistor is a 10 kilo ohm resistor, only that here you can see the color, but that's 10 kilo ohm resistor. So we have a 2.2 nanofarads and a 10 kilo ohm resistor there. Right, and these I've also checked with other capacitors using a meter. This is a 10 nanofarads capacitor. This should be polypropylene capacitor or plastic capacitors. Then this is a ceramic capacitor, 10 nanofarads also, right? And then the range of the MOSFETs that I have used, you can see that one is a K3878, that's 2SK3878 MOSFET, and its capacitance is 4.27 nanofarads are using 1 meter, and then well, it varies with the meter depending on the tolerances. Okay, right, and then the next MOSFET is actually a 20N50, that's a 20 amp 500 volts MOSFET. The other one is an IRFP 250 MOSFET, and then the IRF 740, and then the FXN28 N50F MOSFET, that's a Chinese MOSFET, that one. Okay, and then this is a XP20N50 MOSFET, and then this is a high current low voltage MOSFET, that's a 042N10 MOSFET. Okay, so what I'll do is I'll use one MOSFET. I'll select one MOSFET, and then I'll demonstrate how we can use it as a capacitor. Okay, first we have the results of the 2.2 nanofarads capacitor, and then we have the results for the MOSFET as a capacitor. Right, I'm going to use electronics oscilloscope, and this is my oscilloscope. Right, and the time to measure the frequency there. We have a frequency output that will measure and then compare with a proper capacitor, and then we compare with the MOSFET as a capacitor. This is my power supply. I'm going to use this power supply at 12 volts. Okay, that's the power supply I'm going to use. Another output there, 28.6 volts. Okay, so we're going to use 12 volts power supply to power the circuit. Right, so how we are going to check. First we check the capacitance. I'm going to use this meter and also that meter. Okay, so I have 2 meters to compare so that we can check the capacitance. This is how I got these capacitances of the MOSFETs. Okay, measure together. So first with this meter, I'll show you. Okay, we measure at the gate against the gate against the drain and source actually put together. Okay, or connected together. Okay, right. So this is how we measure. Okay, measure. Let's choose just one MOSFET here. Okay, that's one MOSFET. Okay, not easy to measure. Okay, so here is the gate and drain and source together measured, and that's the capacitance 5,79. Okay, 5,79. Okay, that's maybe the tolerance here. I've written 5,81. That's with this meter here, the yellow meter, and then with the red meter on the same MOSFET. Okay, this red meter on the same MOSFET, and it's actually put on capacitance there. You can see that it's on capacitance. This one also, you can see that it's on 20 nanofarads. This one is auto ranging on capacitance. Okay, 100 millifarads. Okay, and then we check how much is the capacitance on this meter here. Okay, too much reflection on my light there. No problem. Right, on the same MOSFET, I'm going to measure. Okay. Okay. Right. Okay. With that, with the other, I got 5,81. Okay. And then still measuring there with this meter. That's you can see that about 6,1 nanofarads there. Okay, 6,1 nanofarads. That's 6,091 nanofarads. That's the capacitance of that MOSFET. So this is how I confirmed the capacitance is using the meter, right? And also I was confirming with the normal capacitors. Okay, okay, so that I know that my measurements are actually within specs, right? So we are going to power this board using the capacitor, the normal capacitor, and get the results. Okay, I'll be back. Let me connect my scope and power supply. Then I'll show you the results. We have to actually record the results and then compare with the MOSFET. We're going to use one capacitor, this one, and then one MOSFET, so that it actually refers to all other MOSFETs. Then we can actually have recorded the results and compare. Right. Okay, here is the ripple of the input to the end gate, and this is the capacitor, the normal capacitor, 2,2 nanofarads capacitor, and you can see that ripple is a triangle wave, and it's a nice triangle wave. And on DC, the scope is on DC. Okay, it's DC coupling, and the zero line is here. Okay, so that's where the zero line is. And then if I go up there on DC, you can see that it's moving from here. Okay, and the scope is on 2 volts per division. Okay, so that's the 2, 4, 6, so it's centered on 6 and it's going up by maybe 1 volt. Okay, that's about 1 volt up and then 1 volt down. So the NAND gate, because it's a Schmidt trigger, it charges by 1 volt and says the input is now high, and then starts to switch, and then the output comes low. If you check the circuit for the oscillator, and then starts to discharge, and then goes down by 1 volt. If it goes down by 1 volt, it says now the input is low, it switches to high output, and then that's the oscillation. Okay, if I go on AC coupling, you can see the triangle is there, centered on 0, and then let me reduce my force per division, so that we have a very high signal that is we can actually see. So that's the triangle. And if we check, if we want to check the frequency, okay, we position it so that we can check the frequency. So that's from here to there. Okay, so the time per division is 2 microseconds per division, right? So that's our time scale. So we have 2, 4, 6, 8, right? That's about the center is 9, so that's about 9.5. Okay, 9.5. Okay, somewhere there, 9.5, around 9 microsecond. That's the input to the NAND gate, but the capacitance is the normal capacitor. This 2.2 microfarads, 2.2 nanofarads capacitor. Okay, that's the capacitor I'm using. Okay, that's giving us that second, and our input power supply, remember, it's 12 volts. Okay, that's 12 volts power supply. So that's why it is on 6. If you check the data sheet of the 4093, where the IC says it's now high and low, it's around the half the voltage. That's why you find the ripple is oscillating around 6 volts. Okay, so that's our capacitor. We compare it with the Mosfet capacitance, and that's the signal input to the NAND gate. You can check. Okay, compare the merits of that signal. Okay. Right, I have connected circuit to the scope. Okay, so this is the output to the scope, and here is the negative, and then okay, this is the positive. Okay, the positive supply from my power supply. Okay, that one's that red one going to the power supply. Okay, and then the black one. Okay, the black one is on this blue wire. Okay, on this blue wire, that's the negative. Right, so okay, and so here with this capacitor, the frequency is like that. Okay, that's our frequency. Okay, that's a pointer. That is our frequency. That's the output of that circuit. Okay, right. My graduation, the force per division. Okay, this is I'm using channel number 1, input number 1 there. It's on what? It's on 5. Okay, that's on 5 volts per division. Okay, that's 5 volts per division, right? And then my time scale is on 2 microseconds per division. Okay, that's the time per division there, 2 microseconds per division. Right now, okay, now I am going to try to calculate the frequency. Okay, of that circuit, the frequency of that circuit. So let me adjust, try to adjust the positioning there. Okay, right, I'm going on the leading edge. Right, problem with the lighting there. Right, so it's a two microseconds per division. So we are starting here. That's 2, 4, 6, 8. Right, this whole thing is a 2. So that's about a two divisions of that 2 microseconds. Right, so it's a 8.8. Yeah, that's about 9. Okay, so 9 microseconds with a 2.2 nanofarads. Okay, so with a 2.2 nanofarads, we take a comparable MOSFET and mount it. Okay, I'll be back when I mount the comparable MOSFET, and I think the best would be this one, the 2.45 nanofarads MOSFET. Okay, 2, nanofarad, 2.45 nanofarads MOSFET. So we are going to use 2.45 nanofarads MOSFET. Right, so let me confirm the capacitance using the 2 meters. Okay, confirm the capacitance using these 2 meters, this one and that one. I'll start with the red one. Okay, measure the capacitance of that MOSFET. Okay, measure the capacitance of that MOSFET. So as you can see, drain and source together and then get on its own. Right, that's 2.685 nanofarads with this red meter, and its own capacitance there. Right, I try with the yellow one. Right, measure. Right, so with the yellow one is 2.44 nanofarads. Okay, yellow one 2.44 nanofarads. Okay. Right, so I've actually mounted the MOSFET, the 2.45 nanofarads capacitor MOSFET. Okay, right. Now let's check what the frequency is. Okay. Right, and now here is the oscillation at the input of the end gate, and as you can see, a nice triangle wave. That's a nice triangle wave. Okay, I've put my scope on DC. Okay, that's DC, and if you check the ground, there is the ground here, the 0 line. That's the 0 line, and then it's rising up to okay, that's from 0, and my volts per division is on 2. Right, on 2. So we have 2, 4, 6 at the center of the triangle there. So it's going that much from the 2, from the 6, and then that much down. So it's oscillating here. So it's getting to a level where it says the input is now a high, and then it switches back to a low, but with the time for the capacitor to charge. And this is the MOSFET capacitance. Okay, that's the MOSFET capacitance. If I go on AC, you can see the ripple on AC. Okay, let me put on 0, but we know we are going on a good reference. Okay, so that we zero on our reference, put on 0 line there, and put on AC. You can see that's the AC. Okay, that's the ripple. Increase. Okay, let me increase. If I go on that's 0.5 volts per division. That's our oscillation there. Okay, nice oscillation. Okay, and the frequency, you can actually check the frequency will be equal. So that's our frequency. Okay, from here to there, that's on 5. That's on 5 microseconds per division. Okay, 5 microseconds. So that's 5, 10. That's about 12 microseconds. Okay, that's the Mosfet oscillator. Okay, this Mosfet oscillator. Right. So now that it looks evidently that the frequency is lower, meaning that capacitance is higher. Actually, so it differs from the measured capacitance. So I reduce the frequency per division, the time per division, so that we can measure it proper. Okay, move the time per division, the time scale, so that we can see. Now I am on 5 microseconds per division, right? So 5 microseconds per division. I have a time scale there. Move it a bit. Okay, that will be 5. Okay, it's not properly in position. That will be 5, 10, right? That will be half of 5, that's 2.5, 10, 12, around 12 microseconds. Okay, that will be around 12 microseconds. 5, 10, yeah, around the 12 microseconds. So the MOSFET is giving 12 microseconds. So there is a time difference there. That's 12 microseconds at this MOSFET. Okay, and that MOSFET is actually an IRF 740. Okay, that's an IRF 740. But the frequency, as you can see, it's very stable, right? And if I do this, okay, I will add the capacitance, and we check what happens to the frequency. I'll add the capacitance like this, put together like this, and then we see what's happening. Right, so as you can see, if I do this, let's see what happens with the frequency. Okay, so if I add the capacitance, the frequency, it's divided by 4 times frequency actually, so it reduces the frequency 4 times. Okay, I'm actually adding this 042N10 MOSFET. Okay, 042N10 MOSFET. That's the MOSFET that I'm adding. Okay, and I'm adding it to that capacitance, and this is measured capacitance 7.6 nanofarads. Okay, 7.6 nanofarads. That's the capacitance. It is measured using a meter. Okay, so but you can see that the frequency is very, very stable. The oscillation is very, very stable. Okay, that's the oscillation of the MOSFET. Okay, yeah, so a MOSFET can be used as a capacitor, that capacitance. Of course, bear in mind that the maximum voltage is actually 20 volts. That's for low voltage, because the gate voltage, the gate to source voltage is 20 volts. Maximum is 20 volts, and it don't matter. It has no polarity. You can put it either way, no polarity. So yeah, that's our MOSFET as a capacitor. Thank you.